Let's talk about one-to-one functions and their inverses. So we've seen how to take an inverse function algebraically, but I want to talk about what functions have an inverse and which functions don't. So I'm just going to give us a set of numbers to start with here, and we're going to apply this function f, which squares my values, and we're going to get our outputs on this side. So on this side I've got my inputs, also known as the domain, and on this side I've got my outputs, also known as the range. So when I take something like 2 and I apply f to it, I'm going to do 2 squared, and that's going to land me on 4. If I do something like, -1, I'm going to square -1, and that's going to land me on 1. And so on. So 5 then lands me on 25, and you get the idea. So that's what f does. If I want to apply f inverse to undo this, I would think about f inverse. Let's see, what would undo a power 2? That would be a square root. So I'm going to put a question mark here because we're going to see actually why this isn't a function. Well, why it doesn't work anyway as its inverse function. So if I apply the square root to get back, I would do the square root of 4. So let's try and get back. So I'm going to start with a 4, and I'm going to work my way backwards to get to a 2. Well, that works, doesn't it? Because f inverse of 4 should get me back to the 2. The square root of 4 is equal to 2. Let's try it on this one. So now let's do what we think is the inverse function applied to 1. I should be able to get back to my original value of -1. This would be the square root of 1, but remember this is my principal square root. The principal square root does not give you negative numbers back. If you're unsure, type this exact operation into your calculator. It will only give you 1, not plus or minus 1. Which means I'm not able to get back to 1 as a negative. I could get back to 1 as a positive number, so I can draw another arrow here and put a 1 there. So what we're able to do is we're able to get back to some numbers over here on this side. Anything that's positive we can get back to with this principal square root function, but I can't get back to anything like this -1. If I had a -4 here or a -3, my inverse function would not get me back to any of those negative numbers. So this means that my function is not 1-to-1. It's actually 2-to-1. I've got two values here, the 1 and the -1, that give me an output of 1. Okay, so we can look at that with the mapping. Look how messy my mapping is. There's a much simpler way to test if something is 1-to-1 or not 1-to-1. This is not 1-to-1, and if I put a square around these two numbers both map to 1. Okay, so that's the problem. So let's take a look at this graphically, though. It's so much simpler to test to see if something's 1-to-1 graphically. This one's not 1-to-1. Not 1-to-1. Okay, I'll just shorthand it there. If I look at it graphically, let's see, the graph of x squared, that's a quadratic function, so that's going to graph as a parabola. So if I graph this one, I'm looking to see if it's 1-to-1. To be 1-to-1, that means that I can only use one x value for each y value. Well, we were looking at the values 1 and -1, 1 and -1. Those both map up to the same height or the same y value. Both of those give me a value of 1. Do you see how these are lined up horizontally? I can test for 1-to-1 using a horizontal line test. A horizontal line will pass through the points that give me that same, oh, I missed my negative, that give me those same inputs that match to a single output. So I can instead just apply a horizontal line test. So this particular function, f of x, fails the horizontal line test. And in this case, it means that at most places we have a 2-to-1 function. Both the -1 and the positive 1 give me, those are x's, give me an output or a y value of 1. So because it fails the horizontal line test, it is not 1 to 1. So not 1 to 1. 1 to 1. This is important because if it's not 1 to 1, that means it doesn't have an inverse function. Remember up here with our square and our square root, I could get back to some of the numbers. I could get back to any number that was positive, but I couldn't get back to any of the negative numbers. So I don't have an inverse function that undoes all of x squared. The square root of x only undoes half of x squared. So let's take a look at some more functions to see if we can determine if they're 1 to 1 or not. If they are 1 to 1, this one's not, but if they are 1 to 1, that means their inverse function exists. So we can go up here and say that that inverse function doesn't exist. Okay, so let's look at an example then. So for example, let's take a look at g of x is equal to 2x plus 1. This is a linear function. I'm going to look at the graph. It was really nice to take a look at the graph. It has a y-intercept of 1, so b is equal to 1, and my slope is 2, so we'll think of that as 2 over 1. So to get to a second point, I need to go up 2 over 1. So that gives me a second point, and I can draw the graph of this function. So there's the graph that represents this function. In order to test for 1 to 1, I take a horizontal line, I use my pen, and I check to see if there are any values that have the same y value, any x values that have the same y value. My horizontal line only ever passes through the graph once, so I never have two x values that match up to the same y value. So this particular function is 1 to 1. So I do that initial 1 to 1 check. So is my function 1 to 1? Yes. So if I think of that as step 1, that means that I can go on to step 2 and find g inverse. If it wasn't 1 to 1, if my answer was no, then I would stop. There's not a there's not an inverse function. Well, this one does have an inverse, so let's find it. Let's see, we've got g of x equals 2x plus 1. I'm going to call this y instead. So y is equal to 2x plus 1. And I'm going to isolate that x. So I subtract 1. Y minus 1 equals 2x. I'm isolating the x, or undoing what happened to the x. And I divide by 2 next. Y minus 1 divided by 2 is equal to x. And then I do that x-y swap. So as a review, I isolate the x first. And now I'll do my x, y swap. So I swap these two, and I end up with x minus 1 divided by 2 equals y. But we can call it more than just a general y. What I found was the inverse for my function g. So instead, let's call this what it really is, something meaningful, and that's g inverse of x. Now I want to graph this one as well. So this one happens to be, if I split that 2 up, x over 2 minus 1/2, which means that I have a y-intercept of negative 1/2 and a slope of 1/2. Let's go graph this one. I'm going to graph it on my same coordinate system that we had up here. We'll use a yellow pen this time. My y-intercept is negative 1/2, so negative 1/2 is going to be about here, and my slope is 1 over 2. So I need to move up 1 in the x direction, so I move, or in the y direction, and then positive 2, 1, 2 in the y direction, or in the x direction. Up 1 in the x, over 2 in the y. And I'll go ahead and graph this line. Okay, there it is. It's kind of hard to see, but I want to show you something that happens with this one. We've been talking about this x-y swap. My graph isn't the best, but it's actually pretty darn good if you take a look. I have a mirror image. You see there's some symmetry going on, but it's across a diagonal here. So if I kind of eyeball a diagonal, maybe it's about here. So if I eyeball this diagonal, I'll just draw it with my red pen there. I don't know if you can tell, but if I tip it maybe you can. I've got a mirror image of these two lines across that diagonal. Remember we've been talking about that x-y swap? Well, we actually have the x-y swap here across that diagonal. So you can see my x-y swap here. Let me do another set of functions. I'm actually going to start with a graph, so I'll do another set of functions so you can see that x-y swap. We'll actually put some points into the next one. But I just want you to get familiar with what that looks like. Okay, let's do one last example. I'm actually going to go back to the x squared example. So let's go back to f of x equals x squared, which we know wasn't 1 to 1. So when I use all of x squared, it was not 1 to 1. So that would mean that there's no f inverse in this form. What if I just did half of it, though? What if I got rid of this? And instead, I looked at this function. So I'm looking at x squared, but I'm going to limit my domain so that my domain are all the x's such that x is greater than or equal to 0. So I'm going to look at this half. So if I look at this half, there is an inverse function, because now all of a sudden that means that it passes the horizontal line test. So if I take my pen through it, I never cross more than one point. So this one passes the horizontal line test, which means in this form, f inverse does exist. F inverse does exist. So we can go ahead and find f inverse. As I look for f inverse, I do the same thing that we had done before. So y is equal to x squared. I'm going to isolate x. So I need to undo that. Okay, so the square root of y equals, gosh, technically plus or minus x, right? So I need to decide, do I want plus or minus x? Well, remember how we had that diagonal test. So I had our diagonal here. And in order for my inverse to exist, I knew that it was going to be a reflection across my diagonal. So gosh, look at that. I'm in the first quadrant. Everything's positive. So I want the positive x. I haven't done my xy swap yet, though. So if I do my xy swap, then the square root of x is equal to y. And we will call this instead f inverse of x. Let's take a look at some points on our graphs. I'm going to use brown first. On x squared, I have the point, so x squared, I have the point 1, 1. I also have the point, if I put 2 into that function, I have the point 2, 4. So 1, 2, 2, 4. So I've got those points. I'll label 2, 4 here. If I look at my inverse function, which is below it here, and I look at x, square root of x, when I put a 1 in, I get 1, so I have the point 1, 1. If I put a 4 into my function, I get the square root of 4, principal square root of 4, which is 2. So I have the point 4, 2 on this graph. Let's see, 1, 2, 3, 4, 2 would be about right there. 4, 2. Can you see that xy swap? So 4, where is it? 4 gets me to 2. But in my original function, 2 got me to 4. And I can also see it right here with these points. That's why we do the xy swap. So we've got a couple of things. You need to check for 1 to 1 first. If it is 1 to 1 and passes the horizontal line test, then you can find the inverse function. If it isn't 1 to 1, like this original squared function, then you're done. There's no inverse function that exists.